Today, I will be modeling the propagation of an action potential down an axon. First, we'll look at the neuron. A neuron is a cell specialized for intercellular communication. Neurons are essential in the nervous system. There are two types of nervous systems in the human body. First, we have the PNS, or peripheral nervous system, which connects the CNS to limbs and organs. It consists of the nerves and ganglia outside the brain and spinal cord. Next, we have CNS, or the central nervous system. This consists of the brain and spinal cord. It integrates information received from all parts of the body. Neuroglia are cells of the central and peripheral nervous system that support and protect neurons. A neuron consists of dendrites, which receive a stimulus, a cell body and a nucleus, and an axon terminal, where a stimulus leaves the neuron and enters the dendrites of another neuron. Oligodendrocytes are cells that coil around axons of neural cells. The projections continue as myelin sheaths over the axons. Schwann cells produce myelin. Myelin is an insulating sheath around an axon that consists of multiple layers of neuroglial membrane. The more myelin, the faster a signal will travel along the axon. The axon, the elongated extension of a neuron that conducts an action potential. Node of Ranvier is the bare area of the axon between the sheaths of myelin. Conduction velocity is the speed at which an impulse travels down an axon. There are two types of conduction. First, we'll start with saltatory conduction. Saltatory conduction is the rapid propagation of an action potential between the nodes of myelinated axon. This is the faster type of conduction. Notice that shown in the picture, the signal appears as it's jumping along the nodes of Ranvier. This comes from the Spanish term saltar, which means to jump. Next, we have continuous conduction. Continuous conduction is the propagation of an action potential down an unmyelinated axon. This type of conduction is much slower. Length constant is the distance the potential will travel. Localized current is the movement of a potential charges parallel to the inner and outer surfaces of the membrane. Membrane resistance is a measure of the transmembrane flow of ions. Next, we will move to an action potential and the voltage-gated channels. The intracellular fluid of a cell inside an axon is abundant with potassium and has a slightly positive charge. The extracellular fluid of the cells is abundant with potassium ions and has a slightly positive charge. The inside of the membrane is overall slightly negative. The outside of the membrane is overall slightly positive. With opposite charges inside and outside the cell, there is a membrane potential which causes an excitable cell. An action potential is a change in the transmembrane potential of excitable cells. This is initiated by a change in the membrane permeability to sodium ions. When enough sodium ions are left in the membrane, the inside of the cell becomes slightly positive. Voltage-gated sodium channels allow sodium ions to rush into the membrane when a stimulus is presented and depolarization begins. Repolarization occurs when the voltage-gated potassium channels begin to open and allow potassium ions to escape from the inner membrane. This causes the inner membrane charge to drop dramatically, heading back towards resting potential. And this concludes the propagation of an action potential down an axon. Thank you for watching.